iodine molecules dissociating to form iodine atoms in a reversible reaction. And then we are given the balanced equation, the Kc, and the corresponding temperature. And then 6.1 says write down the meaning of the term reversible reaction. A reversible reaction is a reaction in which not only does the reactants form the products, but even the products form the reactants, right? And then 6.2 says at equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. And then how will each of the following be affected? Choose from increases, decreases, or remain the same. So 6.2, 6.2.1, the value of the equilibrium constant. We know fully well that the only thing that can change the value of the equilibrium constant is the temperature and nothing else. So we will easily say remains the same. And then 6.2.2 says the number of moles of iodine atoms, right? So we have I with the I2 basically, which is giving us 2I, right? So the number of moles of the products are greater than the number of moles of the reactants. And how do we know that? We can see using the balancing coefficients, right? Because we know fully well that the number of moles of I divided by number of moles of I2 will be equals to 2 divided by 1. So the number of moles of I is equals to 2 multiplied by the number of moles of I2. So we know that the number of moles of I are greater than the number of moles of I2. So when we increase the pressure, the system wanna decrease that pressure, right? So it does that by favoring the reaction that leads to less number of moles. And the reaction that will lead to less number of moles is the reverse reaction, because it has the most number of moles, right? So 6.2.2 will say increases. So if it was vice versa and we were decreasing the pressure, then the forward reaction would be favored and we'd have a decrease in the number of moles of I2. And then 6.3 says explain the answer to question 6.2.2 by referring to Le Chatelier's principle. That is basically what I just did, right? What I just explained. The system wanna go back to a state of equilibrium. So if we increase something, the reaction that decreases that something will be favored. So we increase the pressure. So the reaction that leads to the less number of moles will be favored. That is the reverse and more number of I2 molecules. I hope that's clear. And then 6.4 says at 227 degrees Celsius, the Kc value for the reaction is 5.6 times 10 to the minus 12. Is the forward reaction endothermic or exothermic? So let's make sense of the Kc value first. So at 727, right, the Kc value is 3.76 times 10 minus 3. And then now we're told that at 227, the Kc value is 5.6 times 10 to the minus 12, much less than at 727. So we decrease the temperature and the Kc value went down, right? But what does the Kc value tells us? We know that when we want to calculate Kc, we say Kc is equals to basically the products, right? divided by the reactants. That's what we are essentially saying. Although we'll square based on the balancing coefficients and all that, but then this is what we are essentially saying. So if we decrease temperature and the Kc value goes down, it means that now we have less products, right? We have less products. So the reverse reaction was favored by the decrease in temperature. Which reaction is favored by a decrease in temperature? That reaction is exothermic, right? So we're saying that the reverse reaction is exothermic. So that tells us consequently that the forward reaction is endothermic. And the question is asking us to explain whether it's endo or exo, right? The forward reaction. So we're gonna say for our answer endothermic, because we know fully well that the reverse reaction is exothermic because it was favored by a decrease in temperature. And then again, it says fully explain your answer, which is what I just did, right? So when you're explaining your answer, you can start by writing down these K values, explaining that Kc is basically products by reactants, and then you can see that when we decrease the temperature, there is less products, so the reverse reaction is favored. Which reaction is favored by decrease in temperature? That's exothermic. So the forward reaction is consequently endothermic. So let's do 6.5. 6.5 says a certain mass of iodine molecules, I2, is sold in a 12.3 decimeter cube flask at a temperature of 727 degrees Celsius, and we are given the corresponding Kc value. And then it goes on to say, when equilibrium is reached, the concentration of the iodine atoms is found to be 4.9 times 10 to the minus 3 mole per decimeter cube. And then we're supposed to calculate the initial mass of the iodine molecules. So before we go anywhere else, let's have our equation. So we have I2 giving us and getting back from 2I, right? So if we draw our table, we're gonna have the number of moles initial, the change in the number of moles, the number of moles in equilibrium, and the concentration, right? It says that for the concentration of the iodine atoms at equilibrium, we have 4.79 times 10 to the minus 3. So if we have this concentration here, we can then calculate this number of moles here, and then consequently get the change in the number of moles, because initially we had 0 here, right? So now we're gonna say the number of moles is equal to the concentration multiplied by the volume. What is the concentration? It's given as 4.79 times 10 to the minus 3, and then we're supposed to multiply it by a volume of 12.3. So if we do that, we're gonna get 0.058917, right? Is the number we get in here, 0.05817. So from 0 to 0.058917, it means we had a change of plus 0.05817. And then as a consequence, if we have a plus on the products, then we're supposed to have a minus on the reactants, right? Initially, we don't know the mass of the iodine molecules, so we cannot calculate the number of moles. But what we can do is just put n instead, right? And we're gonna solve it when we go forward. So here we're gonna have minus 0.05817 divided by 2. What is this 2 here for? This is because for I, we have a balancing coefficient of 2, and then for I2 we have a balancing coefficient of 1. So if you do that, so we have in 0.05817 divided by 2, so we're gonna have n minus 0.02985, right? And then the volume is 12.3, so here we're gonna have n minus 0.02985 divided by 12.3. So now that we have the concentration at equilibrium, we can have Kc is equals to the concentration of I to the power of 2, because that's the products, right? Divided by the concentration of I2 to the power of 1, because that's the balancing coefficient of I2. But we are given the Kc as 4.79, actually as 3.6 by 10 to the minus 3, right? So we're gonna have 3.76 by 10 to the minus 3 is equals to the concentration of I squared, which is 4.79 by 10 to the minus 3, divided by the concentration of I2 to the power of 1. That will be n minus 0.2985 divided by 12.3. So basically, for us to find the initial mass, we have to solve for n first, and then we're gonna use n equals to the mass divided by the molar mass to calculate the mass, right? So if we do that, we're gonna have I'll write it as n minus 0.02985 divided by 12.3 equals to 4.79 multiplied by 10 to the minus 3 squared. We have a square here, I forgot to write it. And then we're going to divide all of this by 3.76 multiplied by 10 to the minus 3. So we can actually break this n minus 0.02985 divided by 12.3, right? If we do that, we get n divided by 12.3 minus 0.02985 divided by 12.3, which is equals to this same expression. Nothing is changing, so I'm just gonna duplicate it instead of writing it again. So now we can take this term to the right hand side, so we're gonna get n divided by 12.3 is equals to, I'm gonna just duplicate the term instead of copying it again. So that term plus 0.02985 divided by 12.3. So now I'm going to multiply the left hand side and the right hand side by 12.3 so that I can get the value of n, right? So I'm multiplying this whole expression by 12.3. So n will be equals to, if you do the multiplication, you're going to get 0.105. And now we know fully well that n is equals to the mass divided by the molar mass. So what is the molar mass of I2, right? So we're gonna have 0.05 equals to the mass divided by 127 multiplied by 2. So the mass is 0.105 multiplied by 254, which is equals to 26.6 recurring grams. Steam H2O reacts with hot carbon at 1000 degrees Celsius according to the following balanced equation. And there we have it. Initially, 36 grams of steam at a certain amount of carbon were placed in a 2 decimeter cube sealed container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.2 225 moles. And then 6.1 says define the term dynamic equilibrium. Dynamic equilibrium is the same as chemical equilibrium. It's the stage in a chemical reaction when the rate of forward reaction equals the rate of reverse reaction. Then 6.2 says calculate the equilibrium constant Kc for the reaction at 1000 degrees Celsius. So again, like we did on the other video, if you haven't watched it, subscribe to the channel and go check it out. So we're gonna start by writing the equation down. We have 2 H2O plus carbon in solid form, which is giving us 2 H2 plus CO2. So we're going to draw the table I did on the other video. Please, if you haven't watched it, please go watch it. So we have H2O, we have the carbon, we have the hydrogen, and we have the carbon dioxide. So what we're gonna have first is the initial number of moles, right? And then after we have the initial number of moles, we're gonna have the change in the number of moles. After the change in the number of moles, we're gonna have the number of moles in equilibrium. And then after that, we're gonna determine the concentration so that we can calculate the Kc. So it is said that initially we have a mass of 36 kg for H2O, right? And then the volume is equals to 2 decimeter cube. We know that the number of moles is given by the mass divided by the molar mass. The mass is 36, and then the molar mass for H2O is 18. So what is 36 divided by 18? That is 2 moles. So initially we have, let me change the color so that it's more visible. So initially we have 2 moles of H2O, and then we have 0 moles of H2, and then we have 0 moles of CO2. And then it is said that the amount of CO2 at equilibrium is 0.225, right? So that means that the change was also 0.225. And then for H2, we can determine that by using the balancing coefficients, right? So we're gonna see the number of moles of H2 divided by the number of moles of CO2 equals to the balancing coefficient of H2, which is 2, and then the balancing coefficient of CO2, which is 1. So basically, you multiply the number of moles of CO2 by 2, and that will give us 0.45. And then the same is true for H2O because the balancing coefficient is 2, right? Just like in H2. But then instead of adding for H2O, we're going to subtract, right? 0.45, because at that instant the reaction that was being favored is the forward reaction, right? If it was vice versa, then we're gonna add on H2O and subtract on CO2 and H2. So here we're gonna have 0.45 because we're adding 0.45 and 0. And then for H2O, we're subtracting 0.45 from 2, and that will give us 1.55. And then the concentration at equilibrium, we know that the volume is 2, right? So we're just gonna divide 1.55 by 2, and that will give us 0.775. We divided 0.45 by 2, it gives us 0.225, and then 0.225 by 2. And that is going to give us 0.1125. And then the question would be, why am I not putting anything for the carbon, right? The carbon is a solid, and in chemical equilibrium, we are only interested in gaseous and aqueous solutions, right? We don't regard solids. So now we can write our equation. We can say that Kc is equals to the products, right, divided by the reactants. So what's the products? We know that we have H2, and then we're supposed to square it. Why are we squaring it? We're squaring it because it has a balancing coefficient of 2. And then we have CO2. And then the reactants, we're going to have H2O. And then we also square it because it has a balancing coefficient of 2. And then we don't regard the carbon because, like I've said, it's a solid. So we can go ahead and substitute those concentrations. So for H2, we have 0.225. So we're going to have 0.225 squared multiplied by the concentration of CO2. The concentration of CO2 is 0.1125. So we're going to have 0.1125. And then divided by the concentration of CO2 of H2O, which is 0.775. And then we square it. After we square it, we can then put it in a calculator, and we have determined our Kc. And that is 0.00942. And then we don't have any SI unit for Kc. So now we can move forward. We have 6.3.1. Then it says the graph shows how the rates of the forward and reverse reactions change with time. These are like the really interesting questions. And then 6.3.1 says, give a reason why the rate of forward reaction decreases between T0 and T1. The rate of the forward reaction is decreasing because the reactants are getting used up, right? So we have reactants are getting used up. And then 6.3.2 says, what change was made to the equilibrium mixture at T3? If both a forward reaction and reverse reaction are favored, they all go up at the same time, then a catalyst was added, right? So they added a catalyst. That is the only way both forward and reverse reaction can be favored at the same time. 6.3.3 says, is the forward reaction exothermic or endothermic? You can see that at T2, forward reaction shoots up, right? It goes up dramatically, and then it eventually starts going down because the reactants are starting to get used up. So at T2, the forward reaction is favored by the increase in temperature. And we know that an increase in temperature only favors endothermic reaction. So we're going to say 6.3.3, the forward reaction is endothermic. Why are we saying it's endothermic? We're saying it's endothermic because it was favored by an increase in temperature. And that's only true for an endothermic reaction. And then 6.3.4 says, refer to the chartelie principle to explain the answer to 6.3.3. That's what we just explained. The forward reaction is favored, and an increase in temperature only favors an endothermic reaction. Consider the balance equation below for a hypothetical reaction that takes place in a sealed 2 decimeter cube container at 300 kelvins, that is. So our hypothetical reaction is happening between 2 atoms of P and 2 atoms of some element Q, which is giving us 2 atoms of PQ, right? I'm calling P not phosphorus and just P because it's a hypothetical reaction. And then 6.1 says, define the term chemical equilibrium. Chemical equilibrium is a stage in a chemical reaction when the rate of forward reaction equals to the rate of the reverse reaction, right? And then 6.2 says the amount of each substance present in the equilibrium mixture at 300 K is shown below in the table. And there we have the table there. And then it goes on to say the temperature of the container is now increased to 350 kelvins. When a new equilibrium is established, it is found that 1.2 moles of P is present in the container. And then 6.2.1 says, is the heat of the reaction positive or negative? So at our initial equilibrium, the amount of the reactants, 2P and Q2, is 0.8 and 0.8 moles, right? And then at 350 K, when the temperature is now increased, right, we have more products. We have more P from 0.8 to 1.2. That tells us that the reverse reaction was favored by the change. So that's why now we have more reactant. So if you increase the temperature, the reaction that will be favored is endothermic, and that's the reverse reaction. So the enthalpy, or the heat of the reaction of the forward reaction, is negative. So our answer for 6.2.1 will be negative, because the reverse reaction was favored by an increase of temperature. If the forward reaction was favored, then we're going to say the heat of our reaction is positive. So 6.2.2 says, use the Chartelie's principle to explain the answer to 6.2.1. I guess that's what I just did. I just, explained 6.2.2 as I was trying to justify 6.2.1. So 6.2.3 then says, calculate the equilibrium constant at 350 kelvins. We know that when we talk about the equilibrium constant, we use the concentration. So the first thing is for us to determine our volume, right? That will help us when we calculate the concentration. The volume is given in the equation as 2 decimeter cube, right? So that's something to note, because we're going to use that all the way going down. So now that we want to calculate the Kc, the equilibrium constant of the reaction, we have to form some sort of a table so that we can end up calculating the quantity at equilibrium. So what we're going to do, we're going to say 2 atoms of P plus 2 atoms of Q, they're giving us 2PQ. And then let me take out my ruler and just create that table. Yeah, so there we go. And then we have our initial number of moles, right? It is given on our table at 300K. For P, the initial is 0.8. And then for Q, it's also 0.8. And then for PQ is 3.2. And then we are told that at the new equilibrium, for P, we have 1.2. So here we'll have our change, and here we'll have our equilibrium concentration. So we are told that here at equilibrium for 2P, it's 1.2. So what's our change? If we find the change for P, then we can use the balancing coefficients to find the change for everything else. And then from there, we can find the concentration. We get our formula for Kc, we sub it in, and then we're basically done with the equation. So the change for P, to determine it, we'll subtract the moles at equilibrium by the initial moles. That will be 1.2 minus 0.8, which will give us 0.4, right? So if you wanna find the change, you subtract final from initial. Only makes sense. You do the same in physics. If you wanna find the change, you subtract the final by the initial. So now that we know the change for P, we can use the balancing coefficients to find the change for Q and the change for PQ. So we can see that for P and Q, for every is a 2:1 relationship. So let me just write that. So we have the number of moles of PQ, right? If we divide them by the number of moles of Q2, the balancing coefficients will be 2 divided by 1. So if you wanna find the change for Q, you divide the change for P by 2. So 0.4 divided by divided by 2, that will give us 0.2. And then for P and PQ, the balancing coefficients are the same. So in our equation here that we establishing, we just gonna, this was supposed to be P and not PQ. So here for PQ, we just gonna have 2 divided by 2, which is just 1. So the change for P and the change for PQ is the same. It's also 0.4. So for Q2 at equilibrium, we'll get 0.8 plus 0.2, which will give us, which is gonna give us 1, right? And then for PQ, we're gonna have 3.2 minus 0.4, which will give us 2.8. So why are we saying for Q? Why are we saying that for Q it's a plus and then for PQ it's a minus? Okay, this is what's happening. We have a reaction. If the products are increasing, the reactants are decreasing. So it is clear that the reactants are increasing, right? The reverse reaction is being favored. So for all the reactants, the change will add it to find the moles at equilibrium. But then from the products, because the reverse reaction is the one that's being favored, meaning that the products is getting depleted and is forming the reactants, we're gonna have a minus instead. So that's why we're not saying plus 0.4, but we're saying minus 0.4, which is thus giving us 2.8. So when we get to this step, all we are left to do with is to find the concentration, and then we can substitute it in our equation. So we have already established that our volume is 2 decimeter cube. So for 2P, we're going to say 1.2 divided by 2, that will give us 0.6. And then for Q2, it will be 1 divided by 2, which will give us 0.5. And then for 2PQ, that will be 2.8 divided by 2, which will give us 1.4. So at this step, we can then say Kc equals to the products, the concentration of the products divided by the concentration of the reactants, right? And then this will be equals to the concentration of PQ squared. Where is the squared coming from? The squared is the balancing coefficient. When you put the concentration, you have to square it by the balancing coefficient. So for Q, which is in the denominator because it's the reactants, you can see that the balancing coefficient is 1. So we're just going to say to the power 1, or you don't have to write that because it's always assumed true. And then for P, we're going to have P to the power of 2 because the balancing coefficient is 2. So what's the concentration of PQ? That's 1.4. So we have 1.4 squared divided concentration for Q2 is 0.6 squared, and then the concentration for P is 0.5. And then after that, it's just a matter of putting it in the calculator, which I'm gonna do real quick. So we have 1.4 squared divided by 0.6 squared multiplied by 0.5, which is equals to 10.89. And then we don't have any units for KC. Another thing to be aware of is that when we writing this formula for KC, we only regard reactants or products that are in gaseous or aqueous form. We don't consider solids. Okay, so that is that for that question. Let's move ahead. 6.2.4 says, how will the equilibrium constant in question 6.2.3 be affected when the volume of the container is decreased at constant temperature? Choose either increase or decrease or remain the same. Give a reason for your answer. It will remain the same. Let me just write that down. So it's gonna remain the same. It will remain the same because only temperature can change Kc. That's always true. Only temperature can change Kc, because if we increase or decrease the volume, then we have done that for both the reactants and both the products. So if it slows down the forward reaction, it's also going to slow down the reverse reaction equally. So Kc at the end of the day is going to remain intact. The only thing that affects Kc is the temperature. 6.3 says more Q2. Q2 is a reactant. So the reactant Q2 is now added to the reaction mixture at a constant temperature. How will each of the following be affected? Choose from increase, decrease, or remain the same. PQ. PQ is a product, so it's gonna increase, right? Because if we increase the reactants, then the forward reaction will be favored, so that we can establish our state of equilibrium. So the yield of PQ will increase. So basically what I'm saying is that if you increase the reactants, then the yield of the products will increase. If you increase the product, then the yield of the reactant of the reactants will increase, so the reverse reaction will be favored. And then 6.3.2 says the number of moles of P 2P and Q2, and then they're saying we increased Q2, right? So what will happen to P? The number of moles of P will go down, because the forward reaction will be favored if you increase the reactants, right? So 2P will be getting depleted at a higher rate. So for 6.3.2, that will be decreases. The following equation represents a key reaction in the preparation of sulfuric acid. The process of the reaction is controlled in such a way that the temperature inside the container remains between 370 degrees Celsius and 550 degrees Celsius at all times. 6.1 says, what is represented by the double arrow in the equation? In chemistry, we know fully well that if we have a double arrow, it simply means that the reaction is reversible, right? So 6.1, you just write the reaction is reversible, and you get your 1 mark. And then 6.2 says, why is this reaction known as the contact process? It is known as the contact process because the reaction occurs in the presence of a catalyst, right? So the reaction is in contact with the catalyst, and therefore is known as the contact process. Now the question you might ask is, which catalyst do we need for this reaction? We need vanadium oxide, right? So the catalyst for our contact process is vanadium oxide, spelled vanadium oxide. But that's not what the question is asking us. The question just wants us to explain that it is known as the contact process because you are in contact with a catalyst, and you get your 1 mark. And then 6.3 says explain what the temperature is preferably not, and then 6.3.1 lower than 370 degrees. So they're telling us that for this reaction we need the temperature to be at least greater than 370 degrees. We need the reaction to be greater than 370 degrees because if the temperature is too low, right? If the temperature is too low, then the yield from the reaction will not be enough, right? Because you know that to increase the reaction, right, we need to increase the temperature, right, so that our yield can go up, right? So the temperature, if it's too low, the yield won't be enough. 6.3.2 says explain why the temperature is preferably not higher than 550 degrees Celsius. Let's look at our equation. Delta H is less than 0, right? So if you increase the temperature too much, then the reverse reaction will be favored. So you'll be basically converting your products back into reactants. And that's not what we want to achieve, right? So you must keep the temperature high enough, but you must not make it too high, because now the reverse reaction will be favored and we will get the reactants again. So here we're saying that a high temperature favors an endothermic reaction, right? A high temperature temp favors an endothermic reaction, right? Endothermic reaction. And then clearly the reverse reaction is endothermic, right? So our reverse reaction is endothermic. So if we increase the temperature, less products will be formed, right? So we're gonna have less products being formed. And then let's move to 6.4. 6.4 is saying for the process above, the following information is obtained from the analysis of the equilibrium mixture at 400 degrees Celsius. The volume of the container is 200 decimeter cube. The initial quantity of SO2 is 50 moles. And then the equilibrium quantity of SO3 is 22 mole. And then the Kc at 400 degrees Celsius is 7.328. Use the information above to calculate the initial mass of oxygen that was used for this reaction. So we're still going to follow the usual technique we use when we want to find Kc, right? But then the only difference here is that we're going to have a value for Kc. We're going to be solving for the oxygen, basically, right? For the number of moles of the oxygen. And then from the number of moles of the oxygen, we're going to be able to determine the mass, therefore. So we have 2SO2 reacting with O2, and then this is giving us 2SO3. We know that the reaction is reversible, so let's have that there. So here we need the initial number of moles, right? Here we need the change, and here we have the moles, at equilibrium, right? And then here we have the concentration. So initially we had 50 moles of SO2, so there goes our 50. And then for O2 we're not given, right? That's what we need to find so that we can consequently find the mass. And then for SO3 we're starting with 0, right? And then at equilibrium we have 22. So at equilibrium for SO2 we have 22, right? So the change here was plus 22. So now we need the change for O2, right? The balancing coefficient here is 2 and here it's 1, right? We usually don't write it, but we know there's a 1 here. So we basically divide in 22 by 2, which will give us 11, right? So if we were given 11 here and we're finding the number of moles of SO3, then we're gonna multiply by 2. For SO2, the balancing coefficients are the same, so we're gonna have 22 here, but we're converting the reactants to products, right? So here we're gonna have minus 11, here we're gonna have minus 22. So what is 50 minus 22? That is 28. And then what is x minus 11? X minus 11. And then now the concentration at equilibrium, right? So we divide in by a volume of 200 decimeter cube. So we have 28 divided by 200, x minus 11 divided by 200, and then we have 22 divided by 200. So now we can see that the Kc is equals to the concentration of the products divided by the concentration of the reactants. So if we go on with that, our product will only have SO3, right? So we're gonna have 22 divided by 200 to the power 2, right? The balancing coefficient divided by the reactants. So we have 28 divided by 200 for SO2, right? To the power 2 multiplied by x minus 11 divided by 200 to the power 1, the balancing coefficient. But we given the value of Kc, we know that it is 7.328. So now we have to solve for x. How are we gonna do that? What we can do here, we can say that x minus 11 divided by 200 is equals to 22 divided by 200 squared divided by 28 divided by 200 squared multiplied by 7.328, right? This step here might be confusing to some, but it's mathematically true, right? You can check it out and see if it works. So every time when you're solving a question like this in Kc, you can just take a term in the denominator and swap it with the term on the other side of the equation, right? It's true. And then from here, so let's multiply both sides by 200 so that we can get rid of this 200 here, right? So if we do that, we're gonna have x minus 11 is equals to 22 divided by 200 again squared divided by 28 divided by 200 squared multiplied by 7.328, and then we multiply in everything by 200, right? So now you can see that you just add 11 to both sides and you determine x. So if you add 11 to both sides, so let's take this entire expression, right? And then we say plus 11. So now we can erase this minus 11 here. We get x being equals to 27.849, right? So now we can use those number of moles to calculate the mass of O2 initially, right? So we know that the mass is equals to the number of moles multiplied by the molar mass. So that will be 27.849 multiplied by 16 multiplied by 2. Yes, so that will give you 891.167 grams. This is a bit lengthy. You can rewind the video so that you can get more clarity. So 6.5, last but not least, says the temperature for the process above is increased to 500 degrees Celsius. Consider the graph, and then there we have a graph. Which reaction, forward or reverse, is represented by the dotted lines? First of all, let's focus on the reverse reaction. We know that the reverse reaction is endothermic. So when we increase the temperature, the reverse reaction should be favored the most, right? More especially above 500 degrees Celsius. When we close to reaching that 550 degrees Celsius, we're not supposed to reach for this reaction because the products will be too little, right? So when we increase the temperature, the reverse reaction will be favored, but the forward reaction will also be favored, but the reverse reaction will be favored more because it is endothermic. So hence the dotted line and the other line, they all go up, right? But you can see clearly that this solid line goes up way above the dotted lines, right? So it is more favored. Hence the solid line is the reverse reaction. So the forward reaction is the dotted line. So the question is asking us to determine which line is the dotted line. The dotted line is the forward, right? Because we know that the reverse will be favored more than the forward if the reverse reaction is endothermic.